Welcome everyone. In this video we are going to analyze a system called Ballistic Pendulum. Now, this system consists of a bullet, as you might have guessed from the ballistic, and a pendulum sort of object, which you could have guessed from the pendulum. So the setup is like this. Let's say that we have a ceiling here, and a block is going to be hanging from the ceiling, and we are assuming that the rope is massless, and it is going to be connected to this capital M. This is the object. Let's say this is the ground. The gravity is going to be downwards. The gravitational field strength G is downwards, and there is going to be a bullet that is traveling towards this pendulum. Let's say that the bullet is like this. It has a mass M, and it is traveling in this direction with velocity v naught. Let's say this is the initial velocity, and the mass is going to be at a height of h initially, just like the bullet. I want to point out that there seems to be a difference, like a distance between the two masses. As you can see, I'm referring to this distance, and yes, it is there. However, notice that I in fact drew this picture so that it is exaggerated. The distance is in fact very small. What I'm trying to say here is, if this is the picture of the system at time equaling 0, once we start the timer, the bullet is not going to accelerate downwards. Normally it would, because there is a gravitational pull downwards. However, we are assuming that the bullet is very close to the mass, so that it is not displaced in the vertical at all. Its whole velocity is in the horizontal. That's the assumption that we are making. It is not a pretty bad assumption if we are shooting the bullet from a nearby place and the bullet is going to be traveling at a high speed. And in fact, we will derive a formula for the initial velocity of the bullet. Okay, this is an important thing to understand. The bullet is going to be directly hitting the mass at the same height as I have drawn it here, because the distance d, let's call it, and I will erase this since we won't use it at all. This distance is very small because, as I said, we are in fact drawing the distance exaggerated. The bullet is very close to the mass and it is very fast, so we can neglect the change in the velocity which occurs in the horizontal direction. And of course, the vertical direction. The change in the vertical direction, we ignore it. And also we are ignoring air resistance. That's the thing to keep in mind. Okay, so what's going to happen? The bullet, many things can happen, right? Well, maybe not many, but you wouldn't expect first of all, the bullet it's not as fast as we want it to be, and it can't, it can't stick to the block, and it will fall off. It will bounce a bit and then it will fall off. That's not the case we're considering. The second case is that the bullet can go straight through the mass, and that is I think that you might even see some problems about it. That's also a common problem that is considered. However, we're not also considering that. What we're considering is the situation when the mass is embedded into the other mass. So the bullet is going to hit the block, hit the pendulum, and it is going to stay inside the pendulum. Okay, that is the case that we are investigating. And in the final case, this is the drawing that I'm making right now. The bullet is going to be sort of like this, embedded, and I want to draw it dashed as well. So, sorry. The bullet is here, it is embedded. And it is, let's say, at a height of, h final, let's say. This was h initial, and that is h final. What we are interested in is actually the difference between the two. So let's just call that delta h, the change in the height, the final height minus the initial height. Okay? And also, one side note, the final height is measured from the ground to the center of mass of the system, of the two body system, bullet and pendulum system, okay? So what I want to find is V naught. How can I figure the value of it? Because, I mean, maybe I am able to measure the height Maybe I am able to measure the height easier than I am able to measure the velocity of the bullet. So I want to find a formula for the velocity of the bullet. Of course, it's going to be in terms of the height. So you can just solve for the height as well, depending on the thing that you're trying to find. Okay? And it seems like a fairly simple question, right? Initially, there is only kinetic energy of the system, 1 over 2 mv naught squared. And of course, we need to maybe include the, initial potential energies, right? So mgh initial plus, let's say it's h naught though. Let's stay consistent with the velocity naming we used. So this is going to be h naught again. Plus mgh naught. This is going to be equal to, the system is not moving at the end, so sum of the masses, gh final. And you can see that this is going to be 1 over 2 mv squared equaling m plus m times g delta h, right? And then we can easily solve for v squared. If you were to say this is false. This doesn't work. Why doesn't it work? You might be asking, like, energy is conserved, right? And no, it is not conserved. It is not conserved from this point to this point because there is a collision. And energy is not conserved in all types of collision. It isn't going to be conserved. Of course, energy is conserved in general, but I need to specify. Mechanical energy doesn't need to be conserved in all types of collisions. And since the bullet is staying inside the pendulum, inside the other mass, this is called a totally inelastic collision. And in a totally inelastic collision, the kinetic energy before the collision is not equal to the kinetic energy after the collision. And the potential energy doesn't change during the collision. So the mechanical energy of the system before the collision is not equal to the mechanical energy of the system after the collision. This conservation of energy equation doesn't work because energy is lost once the two masses collide, because this is a totally inelastic collision. And in a future video, we can also show that in a totally inelastic collision, energy must be lost, mechanical energy must be lost. We can show that there's going to be a loss of kinetic energy, but let's not focus on that in this video. It is also relatively easy to show it. Of course, everything is relative, right? Relatively easy. What am I saying? It is also relatively hard then, right? It depends on what you're comparing it to, okay? Enough said though. And let's do it like this. So this doesn't work. This is very important to understand so that we don't fall to this mistake. Okay, so what do we do then? Well, even though the energy is not conserved before and after the collision, and I keep saying energy, I'm referring to the mechanical energy. Please understand that, okay? My bad. Even though the mechanical energy is not conserved during the collision, after the collision, it is conserved. So we can analyze this thing as it is just colliding, or let's say as it has already collided, as it has just collided. So this is just collided. And then the final case, so I can draw it like this. And the final situation, let's call it. Energy is conserved in this case because the only force is going to be the force due to the only force on the system is going to be the force due to the gravity, and it's a conservative force. There is also the force of the tension, but since it is this pendulum system is going to be traveling, the center of mass is going to be traveling on a circle, and the tangent the tension is always going to be perpendicular to the direction of the velocity. So at this point, let's say like here, the velocity is like this. It is perpendicular. And since the perpendicular force doesn't do any work to the... So if the velocity and the force are perpendicular to each other, there is not going to be any force because we are taking the dot product of the force and the instantaneous displacement while calculating the work. So the tension doesn't do any work. That's what I'm trying to say. I think I overcomplicated the situation. Anyways, so what can we do? Well, if we figure out the energy just after the collision, we can set it up to be equal to the final energy. And for the energy after the collision, just after the collision, we need to find the kinetic energy just after the collision, because we already know the potential energy. And we can find the kinetic energy by using conservation of momentum. The initial momentum is completely in the horizontal direction. It is due to the movement of the bullet. It's going to be mv naught. This is going to equal, so after the collision, the both masses are traveling together. This is again another what do you call, another simplification that we're making. Normally, once the bullet hits the pendulum, it wouldn't immediately have the same speed as the block. Let's call this pendulum a block. It won't have the same velocity as the block because the block was standing still. It will gain some velocity, and the bullet was let's say at initial velocity v naught, so it will lose some velocity, and then they will have the total. At some point, they will have the same velocity. Once the bullet comes to rest inside the block, of course, relative to the mass. And as that happens, once as we are waiting for that situation to occur, for the bullet to come to rest inside the block relative to the block, while we're waiting for that, the height is going to change a tiny bit, okay? But we can, as I'm trying to say, we can ignore that as we're ignoring other factors. So this is the total mass, and this is the final velocity of the system. V final is going to be this then. Okay. Now we can use the conservation of energy for the two cases that I mentioned here. We're going to have m plus m g h naught as our potential energy, plus 1 over 2 m plus m, this is the total mass of the system, and then v final squared, right? So we're going to square this quantity. Let's square those. V naught squared. And this is going to be equal to the final potential energy because there is no kinetic energy. The block comes to the pendulum system comes to a rest at the final position. That's why it is the final position. So the mass is going to be the sum of the two masses and then this. Okay, cool. Now you might notice that the sum cancels. That's nice. And I said that we were trying to find v naught squared. So if I don't know, multiply both sides by 2, so we get rid of this, like so then. And we see, if I factor out 2g here, and if I subtract this from both sides, we're going to have 2g, open parentheses, h final minus h naught, close the parentheses. So we would have 2g delta h. So we have then m plus, squared v naught squared equaling 2g delta h. And now we can solve for v naught squared. It's going to be this ratio squared, and then we have times 2g delta h. Okay? And of course, if you want to find v squared, as we said, we can just erase this square, and just put a square root here. And this is the final result. Also, if you know the velocity, the initial velocity of the bullet, you can you can solve this formula for the change in the height. Okay, that's another possibility. Anyways, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.